Hello, my name is Ved Dhiman, z5480788. This is my video submission for Experiment 1 of PHYS1116 24 Term 3. The experiment I will be discussing today is how do we measure the expansion rate of the universe. In this experiment, observational data about type 1a supernovae were analyzed. These type 1a supernovae were chosen due to their roughly constant negative 19.5 absolute magnitude, which provided a reliable method of determining distance when compared against their apparent magnitudes. The measured recessional velocities of these supernovae, as indicated by redshift, were then plotted against their recorded distance data, producing the highly linear plot seen here. The gradient of the line of best fit, superimposed in red, theoretically corresponded to the value of some constant of proportionality between the distance and recessional velocity, being Hubble's constant. This analysis was repeated for a random sample of 10 observations, and then for a localized sample of observations within 50 megaparsecs, which was correspondent to events from up to 163 million years ago. These varied samples were taken due to the expected temporal locality of H0. If there was a discrepancy in the value of H0 calculated from the local sample and the random sample, but there was a similar linearity in the two datasets, this would greatly support the proposed hypothesis of temporal locality. Comparing the two datasets and their corresponding values of H0 side by side, I made the conclusion that this evidence supported the hypothesis of locality. The value for H0 that I calculated from the local sample of about 66.718 kilometers per second per megaparsec for about 5 significant figures was what I expected to be closest to reality. The depicted chart here, however, produced by NASA's Lambda team 2022, reveals that the accepted value for H0 is contentious, though the average indicated by this gray line is around 67.88 kilometers per second per megaparsec. The most certain result comes from Aghanim et al.'s 2020 analysis of data from the ESA's Planck spacecraft, proposing a value of H0 around 67.4 kilometers per second per megaparsec. Conversely, the value of H0, which would correspond with the accepted universe age of 13.7 gigayears, as proposed by Aghanim et al.'s 2020 analysis of data from the ESA Planck spacecraft, would be 72.532 to 5 significant figures. This discrepancy in values indicates to me that the value of H0 alone is insufficient to accurately determine the age of the universe, though this is beyond the scope of this investigation. If I were to attempt to perform a similar analysis again in future to determine the expansion rate of the universe, it would be important to investigate alternative techniques for determining this, such as those used to obtain the accepted values compiled by Lambda for H0. It may also be of great interest to investigate how the age of the universe is estimated, such as in Aghanim et al.'s 2020 paper, and attempt to derive a value of H0 from this determined age.